Okay, so this is from section 9.6. This is question 65. So it's a poker hand, but it's going to be very similar to the kinds of, the problem that's on the assignment. It's just, instead of dealing with colored cards, we're going to be looking at, actual, like a deck of cards. Now, this particular question is not asking for the probability, but we will also do the probability here because this is just asking for how many ways you can get certain cards. So you basically have to do that, and then to do that in order to figure out the probability of something. So we will start with the full house. So and the book is nice enough to tell us that a full house is 3 of one kind and 2 of another. And so they're giving us an example of that. So when you...
I'm sorry, Stephanie, I joined a little late. Can you tell me where you're getting this example from?
This is from 9.6. This is number 65.
Okay, thank you.
Mm-hmm. So we're going to find how many possible ways you can get a full house, and then we'll also find the probability. So full house is you're doing 3 of one kind and 2 of another. And let's not just do, let's do the specific combination of 2 jacks and 3 aces, because that will be more similar to the problem in the book, where you're looking specifically for not just, oh, how many of this card, but it's like you want this many wilds or this many colors. So this will be more similar to the assignment. So let's say we specifically want a full house with 2 jacks and 3 aces. So we've got the number of jacks. There are 4 jacks in a deck of cards. And so you are looking for a combination that you would pick 2 of those. Now, the order that you pick them doesn't matter. So we're going to be using a combination here. And the way that I think of these problems is it's like it's a counting problem where you multiply your probabilities together in a counting problem. But instead of just having, okay, all 5 cards and multiplying the possibilities for all 5, we do it by category. So we can have a category of jacks and then a category of aces. So the probability, or the number of ways to get 2 jacks, and you're choosing out of, you got 4 possible jacks, is basically 2 choose 4, because that's how many jacks you have. And then there are 4 aces, and you want to know how many ways can you get 3 of them if you're choosing 3 of those. So that would be 3 choose 4. So we're just counting based off of these categories here, the number of jacks and then the number of aces. And it would help if I put these in my calculator in the right combination. So I have a calculator that I use to do the probability stuff. I put mine in backwards. I put in the way that my calculator asks for it is kind of reverse than the way that, wait, I wrote these backwards. I'm being dyslexic today. We have 4 cards, we're choosing 2, and then 4 choose 3. So I'm writing these backwards. Okay, so the number of ways that we can get 2 jacks when we're choosing out of 4 is 6. And then for the aces, it's 4 and we're choosing 3. And there are 4 choices, 4 ways you can do that there. And so that means there are 24 ways to get this specific combination of full house, where you get 2 jacks and 3 aces. So that would be how many ways you can do that. So there are 24 ways to get full house of 2 jacks, 3 aces. Now, let's say you're asked the probability of getting that specific hand. So to find the probability, you need to find how many possible hands are there total. So to find the probability, we need to find the total number of hands. And that is just, you're literally choosing 5 cards out of 52, because we have 52 cards. So the order that you choose the cards doesn't matter. So again, this is just a combination of 52, choose 5. You're taking 5 out of those 52. So I'm going to use my calculator. And 52, choose 5. This gives me a large number. So that's how many total ways that we can get 5 cards out of a deck of cards, out of 52. So we've got that many ways that you get 5 cards out of 52. And so our probability of getting, let's say, a full house of 2 jacks and 3 aces would be our number of combinations over our number of possibilities. We've now taken our number of possible hands, 24, and divided it by the number of ways you can pick 5 cards, and that gives us our probability. So let me just literally divide this. Make sure I have the right number of zeros. So probabilities are not percents. If we want to write it as a percent, we'd basically move your decimal place over 2 places, and then that would give you a percent. So the probability of getting that specific hand of a full house of 2 jacks and 3 aces is very, very small. Let's say I got a hand of 2 queens, an ace, and then 2 tens. So still 5 cards, but we're just looking for a different combination of cards. So in this case, we've got 3 categories. We've got the queens, we've got an ace, and then we've got tens. So there's 4 of each type of card. So we have 4, and we're choosing 2 because we want 2 queens. We want a single ace. There are 4 aces, so you're choosing 1. And then there are 4 tens, and we're choosing 2 of those. So we think about it in categories, and then you put each of those on your calculator, and we already know that 4 choose 2 is 6 because we had to find it out here. And then on the calculator, we need to do 4 choose 1, so that comes out to 4. And then 4 choose 2 is another 6. 4 times 6. And this gives us 144 ways that you can get a hand of 2 queens an ace, and 2 tens. And then the probability of this would be 144 over the total number of card combinations for 5 cards. And again, this is very small. So a very, very small probability, very, very small percentage. But it's more likely than the full house that we talked about. So if it was a percent, it's slightly bigger. Now these are very restrictive problems that we're looking for very specific combinations of cards. But I could say, okay, what if I want 2 queens, an ace, and then I don't care what the other 2 cards are? So we can say we still want 2 queens, we still want 1 ace, and then 2 whatever. We don't really care what those other cards are. So we're still looking at our categories: queens, ace, and then whatever. So we have 4, choose 2, 4, choose 1. And then for the whatever, it's whatever is left over. So it could include queens or aces, any queens or aces we haven't chosen. So there's 52 cards, and we've picked 3 of them already from the 2 queens and the ace. So that leaves us 49 cards, because 3 of them are gone. So we have 49 cards, and then we want 2 of them to come up to a 5-card hand. So that gives us 49, choose 2. So we know the first 2 values. I need to do 49, choose 2 on my calculator. Make sure I don't accidentally hit the permutation button. And that comes out to 1,176. Because we have less restrictions on what those last 2 cards are, there's a lot more combinations, possible cards you can get. So when we multiply that out, we have 28,224 possible ways we can get a hand of 2 queens, 1 ace, and then whatever. And then the probability of this would be the 28,224 over that 2 million number. So those are all the digits I got. If we make it a percent, it's actually over 1%. Still not a good probability of getting it, but that because we're being less restrictive, we have an over 1%, just barely over 1% chance of getting a hand with that combination. Probability. Oops, 1.5. And then these are our choices. Oh. Okay. Let me delete all this other junk here. So a space vehicle has an independent backup system for one of its communication networks. And the word independent there is really important because that It allows you to multiply probabilities together. The fire department one is also independent because the probability of one vehicle being available has no effect on the other vehicle. So they are independent. So a space vehicle has an independent backup system for one of its communication networks. The probability that either system will function satisfactorily during a flight is 0.985. So for each system has a probability of functioning at 0.985. So what is the probability that during a given flight, both systems function satisfactorily, both systems fail, and at least one system is functioning satisfactorily? We've got two events, and we're looking for the probability that both of them are occurring. In this specific example, they're both functioning. It's the same thing with the fire truck, that they're both available. And so they're independent, so we have to multiply those probabilities together. So we have the probability, if we think of them as A and B, the probability that A is working, and then we multiply it by the probability that B is working. And that will give you the probability that they are both working. So the probability of them working is 0.985. So this is 0.985 times 0.985. And it would be something similar with the fire truck. You just have different probabilities. So you're treating these, again, this is like the category kind of thing, where you have two different categories because you have two different vehicles. So you have to treat them each separately, and then you multiply those together.
But where does it say that the second one would be 0.985? Couldn't that be available 100% of the time?
No, it says specifically the probability that either system. So either one is 0.985.
Okay.
And so in our fire department example, they're the same type of vehicle, so the probability that a specific vehicle is available is going to be the same for each vehicle. They're both going to have a 0.9 or 90% probability of being available.
Okay. Gotcha. Okay.
Yeah. So they are both 0.985. So in this particular example, so we multiply these together, and the probability that both of them are available is 0.97, or about 97%. Now, this should be less than the probability of one of them, because it's possible that you can have only one available. To get both of them functioning is going to be, you know, you're not going to have exactly, if one of them is 98.5% available, both of them, you have more things to consider, and so it's not as likely to get that exact same percentage, and so it is going to be lower than the probability of one of them functioning, because now you have more conditions. And when you have more conditions, the probability usually gets smaller because you have more constraints on here. So to have both of them working, that's 97% roughly here.
Okay.
Now, for at least one system function satisfactory, this is the one that usually people start messing up here. Because this is where, so let's think about at least one function, or at least one working. So you've got the probability of one of them working, so like the probability of A, and then B not working. Then you have the probability of B working and A not working. And then you also have the probability that both A and B are working. So it says at least one. And they are different systems, so you have to think about, okay, they're individual. It's not just the probability of A and that's good enough, because there's also what if you have the second system, because these are distinct different systems, but they have the same probability. So the probability of A working and B not working, that's what this is here. So A works, B doesn't. So that would be 0.985 for A working. And then for B not working, it's the complement of 0.985. Because that's the opposite of working is not working, so you have to subtract that. And then you multiply those together. For the probability of B here, this is where B is working, but A does not. So 1 minus 0.985 times 0.985. And then we have the probability that both of them are working, which we've already figured out from part A there. So the 0.97. So you've got multiple things to consider here. So 1 minus 0.985, that's 0.042. So then I'm going to multiply that by 0.985. So we got 0.04137, and this comes out to the same number here. And then you've got you've got 0.04137 plus 0.04137 plus 0.97. And I must have made a math error because I just got something over 100%. Because I got 1.05. So here's the thing about probabilities is you can't get probabilities over 100%. So if you get a probability over 100%, like I just got a number that's over 1, that tells you that you are think you've made a mistake somewhere. That perhaps you are double counting something. So it's usually you're double counting and you have to subtract something, or you've put in too many combinations here. B doesn't.
I was going to say, I think it was your A and B, and then whenever you minused whenever A doesn't work, I think that was where you messed up. I think you took the wrong traction.
That's possible. Let me double check that. Oh yeah, now I'm looking at my calculator. I got a different number there. Okay, 1 minus 0.985 times 0.985. Okay, so there we go. Okay, so now that we're going to actually correct my math. Whoops. So always double check what you put in your calculator, especially if you get something that's impossible. Okay, now let's add these up. Okay, this is much better. I'm like, I know I did the problem, right? What's going on? So this comes out to 0.99955, roughly. It's not exactly 100%, but it's close to 100%. And so this is why they have multiple systems, because as long as the probability that at least one of them is working and is really high, you're good enough. Like here, the probability that at least one system is working is practically 100%. But if you wanted both of them to work, it's less than that. But we don't care about both of them working. It's a fail-safe to have more than one system. So you want to make sure that at least one of them is working, and it's at a high enough probability that you you feel safe that you can have this kind of system. And it would make sense for this particular problem that it's like a NASA kind of problem, that you would want a really, really high probability, like practically 100%, because you don't want to have something fail in flight. And so the fire department's problem is done very similarly, different probabilities, but it's done in the same sort of way, where the at least question mark is really looking at the probability of one working, the other one doesn't, and then the other working, that doesn't, and then them both together.
This is based on experimentation, though, right? It's they just don't throw these numbers out and say, okay, we're going to first assume that we're going to get these numbers, and then we'll check for it. Is that,
yeah, like the original 0.985 is based off of experimentation, based off of whatever they've experienced in all the runs that they've done, or past experience.
Okay.
Yeah, so like in the real world, you would run something and figure out what is the probability of it functioning or failing. Usually you do a whole bunch of statistical tests. You'd usually want to have at least 30 runs, depending on the requirements, and there's a whole lot more like assumptions and everything that you have to learn about in a stats class. But yeah, they will do some number of runs, or some number of tests to determine that probability, and then use that to kind of determine, well, how many systems do I need to get my probability of at least one of them working high enough for me. Like if we had the probability of at least one of them was lower, like if it was the probability of at least one was like 80%, they might say, oh, now I need to have another system, so let's redo the numbers of 3 systems and see how that increases things for us.
Hi guys, so yeah, something else that I'm on. I just wanted to address question 2 here. Both systems fail, so I'm going to do that one right now. So what happens when we have 2 systems and they both fail? So we can do this just like we did the both systems functioning satisfactorily, where you take your 2 probabilities and you multiply them together. But instead of multiplying the probability that they're successful, you're multiplying the probability that they're unsuccessful. So that would be probability of like not A and the probability of not B. That's just some notations, a little curly thing before it, just to indicate like the opposite. I think the book has the complement with a line over, so that's another way that you can write it as the complement, and the complement is just 1 minus the probability. So that's what we're doing here, because the probability of it failing is 1 minus the probability that it is successful. So this is 1 minus 0.985 times 1 minus 0.985. So we're going to do this calculation and make sure that I actually do it correctly in my calculator this time. So that gives me a 0.015 for 0.15. So I'm going to just multiply that out. Okay. And this gives me 0.000225. So that is, let me make sure, I'm just going to double check my math. Minus 0.985 times 0.015, 0.000225. Good. Okay. So that is the probability that both systems fail. very, very small probability, which is what we want in a example like this in space. You don't want you don't want things to fail. You want to have enough fail safes that it is successful. So an alternate way of doing this both systems fail, and I'm going to do this green, is let's think of the total probabilities, like all the possible combinations. So let me just move this down. The probability that both fail, basically none work, plus the probability that like A works and B doesn't, plus the probability that B works and A doesn't, and then the probability that they both work. Those are all of our choices, and if you add up all of those probabilities, that will equal to 1. Now, the probability A works, B doesn't, B works, A doesn't, and the probability of both, that is the probability of at least one works, which we saw in part 3 here. So if you notice this, you could also find the probability that both fail by doing 1 minus the probability that at least one works. So the probability that none of them are working is the complement of at least one working. And so we can verify this calculation and see if we get the same number that we did. 1 minus 0.99955. Now, of course, there's going to be rounding, so it won't be exact. But 1 minus 0.99955. 0.00045, and it's 0.000225. So they are close. It's probably rounding because we rounded in various places. I rounded the 0.97. I'm just going to try to put everything in 0.985 exactly as is, plus 985 squared, 1 minus answer. Okay, yeah, it's definitely rounding because I just did the entire calculation without any rounding, and I got 0.000225. So this is not the same due to rounding, because we rounded that the 0.970225 to 0.97. So because of that rounding, that's why these are not exactly the same. So if we didn't do that, if we didn't round, you would get the same exact answer. So let's show that calculation here. So you're subtracting the 0.014775 and the 0.14775, and then it was 0.970225. So 0.0147775 plus 0.0147775 plus 0.970225. So if you don't round, you get 1 minus 0.99975. So you can see the rounding does make a difference on that. And then 1 minus that, 0.000225. And so that is the same answer that we got up here when we did the complement of each individual. So I just wanted to go in depth there and show you how to find that both of them fail, or the alternative way to do it, which would be the complement of at least one. So hopefully this is helpful for the assignment, and I will talk to you later. Bye.